The topic this week is thus to introduce two new technicalities which we are going to need. One is just serving us as a purpose of defining measurements, and this is the spectral decomposition of an operator. This is normally what I normally call one of these hidden gems of quantum mechanics. And it allows us to actually rewrite equations in a much more compact way. Then, when we're done with that, we are going to look at two simple quantum mechanical systems. These are systems which we can diagonalize with standard eigenvalue solvers. One is an amazing 2x2 matrix, which you can diagonalize by hand, and the other one is a 4x4 matrix. The reason why I've chosen these systems is that we can use a 1-qubit system and a 2-qubit system. And we are going to rewrite these matrices to diagonalize in terms of the Pauli matrices. Because the Pauli matrices play a fundamental role when we deal with quantum computing. And one of the reasons why they play a fundamental role is that many of the gates which we can realize, they are written in terms of Pauli matrices. The Pauli C matrix has actually the states we discussed last week, 0 and 1, as eigenstates. And that is a very important feature which we are going to use when we are going to rewrite Hamiltonians. For those of you who are familiar with many-body physics, you have encountered quantities like second quantization operators. It's a way to rewrite the Hamiltonian. There are transformations of these operators in terms of Pauli matrices, which then can be realized as gates. And you will see that when we move on. But we will start with a Hamiltonian, and we rewrite that in terms of an eigenvalue problem, which means that we will have a Hamiltonian matrix. So I am assuming that these are things you are somewhat familiar with. It's a standard way of rewriting a quantum mechanical problem, like so the solution of Schrödinger's equation is an equation you can rewrite in many ways. You can rewrite that in terms of stochastic methods. You would deal with Monte Carlo machineries. You can invert a matrix, which means solving it via the resolvent. That leads to the technique of Green's function. You can rewrite it as an eigenvalue problem, which means that you have a matrix which is finite, and then we can find the eigenvalues of that matrix. This is where we will start today. This is the, how to say, from a pedagogical point of view, it's the closest we get to the way we will reformulate the system in terms of quantum gates and devices. Okay, so that's the kind of pedagogical motivation for why we want to introduce these exercises and these simple examples. And later, as the first part of the project, you're actually going to rewrite these simulations in terms of quantum mechanical operations with different gates, or rather Pauli matrices. Okay? Any questions so far? So at the end of the slides this week, you will find the first exercise sets. And what I wanted to do now is to give you a quick reminder, a very quick one, of what we did last week. So the first thing we did was a repetition of linear algebra, and I'm not going to repeat that. But what we did, besides a reminder of the Pauli matrices, was a definition of a computational basis. So I'm going to dwell a little bit on this, just a few minutes. And the reason for that is that when we want to realize these systems experimentally, we're actually looking after discrete states in a many-body system. This can be superconducting systems, it can be ion traps, it can be electrons traps in small regions, so-called quantum dot devices, etc., etc. And in all of these systems, these are complicated many-body systems. When you look at textbooks, you often think of these as one particle states, but in general, they are not. They are complicated many-body states, but then we try to, from experiment, to find states which we can manipulate and think of as qubits. And that leads to the introduction of what we will call a computational basis. So in our cases, a computational basis will be a theoretical basis, which is orthogonal and normally normalized. So that means an ONB basis. And last time we discussed some of them, and there's a link there to written notes where we show some examples. Then we defined the simplest possible case. And this is an example of a computational basis. In principle, every real system has an infinity of states. Some states will represent bound states. That means that if you have a trap, you can trap a particle in that small region. And the energy levels which that system has may be some few ones which represent bound states of the system. That means that the particle cannot escape the potential well. Then, when it escapes, there is a continuous range of energies, which are normally called either scattering state or just simply the continuum of states. So what we're doing now is typically to pick perhaps some of the lowest lying states. And for an experimentalist, they're often looking into states where they can manipulate them with lasers. So they will look at states where you can have a one photon emission. And these type of manipulations can then be interpreted as so-called quantum mechanical gates, which we will come back to. So one of the other things which we discussed was actually the projection operators. And we, in this specific case, we have only two states, so the sum runs from 0 to 1. And this leads to the standard definition of completeness given by the identity operator, which simply has 1 along the diagonals. Then we define projection operators. And these projection operators is something which we will come back to today and use again and again and again. And these projection operators commute with each other. They are so-called idempotent, which means that the projection operator squared is equal to itself, etc., etc. So these are properties which we will use quite a lot in the manipulations of quantum mechanical systems. We looked at the superposition. So we can, when we have an orthogonal basis, we can then expand a new function in that basis. So today, when we will be discussing measurements, we're actually going to look at how this state collapses into one of these two states when we make a measurement. So you're going to see this 2-qubit or the 1-qubit example again and again as different examples, because it's simple to demonstrate on the whiteboard or the blackboard, and it gives you an intuitive understanding of what is going on. So many of the examples which I will show later today, they simply use that simple computational basis with a qubit state 0 and a qubit state 1. Or we don't need to call them qubits, we could just call them state 0 and state 1. They don't need to be qubits. Actually, nowadays, there's a lot of technological development in dealing with more than two states. So if you have 3 states, these are called qubits. And then if you go to 4 states, you have Q quartics and so on and so on. So there's a lot of experimental activity going on actually including more states in a computational basis. Then we discussed inner products. We discussed the projection of these operators, etc., etc. So this is just a very quick repetition of what we did. One of the quantities we are going to look at today in more detail is a density matrix. Why the density matrix? Because we are going to look at a measure of entanglement using this density matrix. So that means that we are going to pick a state, psi, and then we define the density matrix as the outer product of that state. Now, in this specific case, that state is a linear combination of computational basis states. In that case, what happens is that we get a density matrix, which when I take the diagonal, the sum of the diagonal elements, which is called a trace, this is simply resulting in 1. We went through some other matrices which we're going to meet. So this is a state which creates a matrix, which we will rewrite in terms of specific quantum mechanical gates, or we will often just call them quantum mechanical operations. And this is something which now takes one of the given states and produces a superposition. So this is going to be very useful when we want to make operations on quantum mechanical systems, and we want to look at the superposition of states, which we then can use in turn to make quantum operations. And then we have some other ones. We discussed tensor products, which is also an important quantity, which you will see again and again. And often when we have, let's say, two states here, when we write it in this kind of compact way, this actually is a tensor product between two states. And I use, from now and on, also actually from last week, we were using this as the representation of a vector. So a vector is given in this Dirac bracket notation. But just read this as just a plain vector. So if you don't like the Dirac bracket notation, you can take it away and just define a bold-face quantity as a vector. Then we have the examples of tensor products, and this is roughly where we ended last time, where we then had states like this qubit 0 with qubit 0, and then we produce a 2-qubit state. You could also think of this as a 2-particle state. It doesn't need to be a 2-qubit state. You could have an electron in state 0 and an electron in state 0, and then you make a 2-electron state, which is now still a basis which constitutes an orthonormal basis. And you see that immediately if you take the inner product between this one and that one, that's going to give you 0. So there are more examples. And the one other reason why I bring this up is that the systems we will look at today, the 2x2 matrix, uses 1 qubit, the qubit 0 and 1. The 4x4 matrix is going to diagonalize the system with these 4 states where I combine 2 qubits. So that's going, you have 4 states. And if I want to find the eigenvalues of an interacting system, as you will see later, I'm going to diagonal a matrix, which is going to be a 4x4 matrix. So you will see these technicalities a little bit later today. Okay, then you can continue. I discussed some other tensor products, and we are going now to switch over to the topic today. And we are going to look at the measurements. But before we do that, we need to introduce a technicality, which is called the spectral decomposition. So I'm going to slow down the pace and move over to the whiteboard, if that's okay. So everything is in the Jupyter notebook, but I like to slow down the pace so that you get some time to think. And it's always boring to look at slides. After 5 minutes, my attention span is gone. So hopefully I can keep you awake now. So let's take a look at let's just switch to the whiteboard and look at this definition of what's called, so here you will also find some definitions of basic Hermitian operators, but we are going to look at the spectral decomposition, and you will see later why this is of interest. So this is a technicality from quantum mechanics, but it's a useful technicality. So have you heard of the spectral decomposition? Yeah, some people are nodding, some are not. So let's remind ourselves about it. So let's do that. So what we are going to look at now is this spectral decomposition. And that is, as I announced, is one of these technicalities which we are going to need. So what we will assume now is that we have a basis, and this basis contains some states which are orthonormal, or orthogonal, and normalized. So we assume that we have a basis, an O and D basis, and I'm just going to call this for a general state I, which is now included in this discrete set of states, 1 up to some states n minus 1. So this is a finite basis. It could represent the bound states of a quantum mechanical system. If you are adding the continuum, you will have an infinity of states. So n should in principle go to infinity. But let's assume that we have a finite basis. Then the next thing we are going to look at now, we are going to assume that this is an eigenbasis of an operator which we call for A, and this operator A acts on this state I, and that has some eigenvalue lambda I of I here. That's the basic assumption which we are making. So the basis here is an eigenbasis of this specific operator, and we haven't specified the operator. The next thing we are going to say now is that we have a state. So when we have an orthogonal basis, we can expand any other state in that basis. So if you have a Hamiltonian problem, a quantum mechanical problem, where a particle is confined to move in a harmonic oscillator trap, but then you have more than just one particle, they will also be interacting, then we know that we could make an ansatz with an orthonormal basis, which is given by the harmonic oscillator. So that would be an eigenbasis of just the harmonic oscillator, but it would not be an eigenbasis of the full Hamiltonian of the system, right? So this is a kind, I'm bringing up this because this is the way we will often devise a computational basis. This computational basis may not be the basis we devise in an experimental setup, because then often we are limited to a many-body system, and then we pick some selected low-lying states and define them as a computational basis. But now we have the freedom as theorists, we have the freedom to define an orthogonal basis, okay? So with that, we can make an expansion. So suppose now I have a state, A, psi of A, and I can make an expansion where I have a sum from I up to n minus 1, and then we have some coefficients Cia of I, which means that this Ci of A, Cai, sorry, these are actually given by the overlaps between the state I with the state psi of A. So if we can calculate both sides, if we have the orthogonal basis and we have psi of A, then we can find the coefficients. This is normally not the case. However, what we also know is that if we have these coefficients, we have a normalization condition, which simply states that Cai, sorry, has to sum up to 1. This is the normalization condition. Okay, so if I now act on this state with this operator A, psi of A, this is the same as us looking at the sum from I equals 0 to n minus 1 of Cai of A of I, which then translates into, since these states I are eigenstates of A, this translates into the eigenvalue multiplied with the state. Then what you should recall is that the outer product of any state vector with itself is just a projection operator. So I can define a projection operator for this state. So when I have a P here, that is going to be reserved for projection operators. And we can always define a projection operator like this. This is an important operation because it will also be included in the definition of the density matrix, which again is important when you're going to study entanglement and link that with a measure which is called the von Neumann entropy. Then what we have a similar one for the states J, this orthonormal basis which we have. This is a similar projection operator, which means that if I act with this operator on Pj, just a moment here, because I can hear that somebody online is, I need to mute some of the participants here. Okay. I got some noise in the background. Okay, so what we can do then is actually to act with this operator on this state, A, psi of A, and then that is the same as J, the outer product of the two states, J, and then we have a sum from I equals 0 to n minus 1, and then we have the CIA and I here, like that. That is the operation of that specific operator. And this simplifies when we look at it and we use a normalization condition. This just simplifies to a sum over I to n minus 1. And then we're going to have the CAI, this overlap. We're going to have the state J. And then we have J with I. And since this is an orthonormal basis, this is just given by the Kronecker delta. And this equation simplifies then to CAJ. I always make an error here with A's and I's and multiplied with the state J. So what we do next now is that we substitute. If we go back a little bit, we can actually make a nice substitution because we have substitute this Pj psi of A with this coefficient, which in this case we can assume is something we can calculate with that expression. So what we do then is that we substitute this term, which you see here, this one, with this one. So let's go back to the expression then, because then what we have is that A acting on psi of A, or psi of A, is equal to I 0 to n minus 1. And then I have my CAI lambda I with this one. And now we can use this definition which we found and then replace this one with this Pj here. So let's do that. And then we can rewrite this as an I equals 0 to n minus 1 of lambda I of Pi of psi of A. Okay? So from that, what we can deduce then from this, we deduce the following. And this is the spectral decomposition of an operator. So what we can deduce then is the following expression, which you will find handy when it comes to definitions of measurement. So what we have then is that the operator A can now be written out like a sum over this complete orthonormal basis, which is a basis of that operator in terms of a projection operator P of I times the eigenvalue. This is something we will see again when we are going to define the density matrices and other quantities. So this is a technicality, and it's called the spectral decomposition of an operator, where what we have done is using what we normally call a normal operator. So we are going to assume that these are emission operators, these are normal operators, and it is true for any state, and is also independent of the basis which we choose. So the question is now, why is this so interesting? Now, for us, it makes a very nice way of describing measurements. So why measurements? Measurements because when we are going to run calculations, and this is what is done experimentally, you will hear a kind of slang, which is called number of shots. So the number of shots is the number of trials. So what you typically want to do when you run a measurement is that you run it thousands of times, and then you calculate the final average. So every time you run on a real quantum computer, you're actually going to run this many, many times, and then you take the average of the final result. So if you have a result which should be 50% exactly from theory, you may get 49% when you run this experimentally. And the more times you run it, the better it is because you accumulate more statistics. So when we now look at measurements, we're actually going to look at how a state, which is a linear combination of many computational basis states, how that collapses into one of the states. So when we perform a measurement, what we're actually going to do now is that the wave function will collapse to a specific state. And these are things which we will use when we are going to run our quantum operations on a given system. So it's not that you run a calculation once, you're going to run it many, many times, and you will pile up all these calculations and calculate the final average by dividing by the total number of experiments which you run. When I say experiments, often people call them shots. Okay, so let's move on to measurements of observables. So when we perform a measurement, this means that we would have an operator which acts in this state, and then we get an eigenvalue or some kind of value. So ideally, this is what we want to achieve, but these states are normally a linear combination, often of a computational basis. So quantum mechanics, if you spool back to some of the basic postulates, so quantum mechanics postulates that the mutually exclusive measurement outcomes, they correspond to orthogonal projections or projection operators. So what we are going to define now is a set of projection operators. And if you remember the basis set which we had, we could now define a P0, which is the same as this projection operator here. We can define a P1. We don't need to have a complete set of operators which exhaust the basis we have. So this M could actually be smaller or equal to the total number of the computational basis states we have. So remember now that this computational basis we have contained a given number of states. So I'm having this numbering from 0 to n-1 because this favors computational languages, computing languages like C++ and Python, where arrays start with element 0. So when we're going to program, it's often easier to just reset everything to 0. If you don't like that, you can change 0 with 1 and start with 1. Okay. So when we now look at this set, yeah. Yeah.
But is this the same list?
It could be the same list, but
it doesn't have to be.
It doesn't have to be.
It could be you bring,
yeah.
And then you take a sample.
Right. Okay. So you can actually define which projection operators you want to deal with. So like when you define the density matrix, you just pick a state and you use that one to define the density matrix. So if you then also keep track, if you look at the identity or the completeness relation here, that is a sum which runs from n-1 over all these projection operators, and that gives you the identity matrix 1 here. So if you think back, one of the examples which we looked at last week. So what we have then is a state 0, and this is given by 1, 0, and the state 1, which is given by 0, 1. And then we have that the sum, if we look at that one, the sum from I equals 0 to 1 of these two states gives us then the identity matrix. And just remind you of like this definition here, which is just 1, 0, 0. And that is the same as the outer product of these two vectors. Just a quick reminder. I hope you don't get offended if I repeat things. I've always been a fan of repetitions. Okay. So when we now define the probability, so suppose we want to find the probability of a specific eigenvalue of a specific state. So we want the probability, and I'm going to write that one as a lambda of I. And we are going to define that probability in terms of an expression which you may have seen before. So we're going to look at this specific quantity. So this is nope, that was wrong. So this is the Hermitian adjoint of psi of A. And we will often just rewrite this one in the following way: P of I acting on the state psi of A squared. And we know that these operators, P of I, the Hermitian adjoint here is equal to P of I. And we know also that P of I squared is equal to P of I. So this probability is actually equal. The probability for finding one of the states is now given by this quantity which we have here. This overlap. So we have an operator P of I acting on this state, and then it ends in a state C of I. So the total probability, so these are just definitions which I'm putting up here. So the total probability has to sum to 1, and we're assuming that the states are normalized. So this means that I should get this relation here. So the probability of these lambdas of i's has to sum up to 1. Yeah. Yeah, yeah. Just that one, right? Because these are idempotent operators. And you can see that immediately if you again go back to this trivial example I've been using. So if you look at the, if you take this one, you know that that one becomes 1, 0, 0, 0. So this is what we would call P0. And then you see that in this case, this is a real matrix. So that means that this obviously is equal to P. And then you see also when you do the operations here, when you square it, it's equal to itself. Okay. So guys, feel free to ask questions. Don't be intimidated. So what we will do after the break is to look at some other definitions, like the post-measurement normalized quantum state, which we get after a measurement, what that one looks like. And we will look at some examples. And then we are going to go back to the slides, and we will look at the Hamiltonian problems, which we will start working with. So in the beginning, we are going to look at these Hamiltonian problems from just a plain eigenvalue point of view. And these are exciting 2x2 and 4x4 matrices. The 2x2 one you can do by hand. So actually, one of the tasks we've been implementing on a quantum computer is to diagonalize a fantastic 2x2 matrix. So you're capable of doing that and you get decent results, but it's not something you would brag about in the next party you get invited to. Perhaps that's the reason why nobody invites me to parties anymore. Right? Okay, let's take a small break. Hey, guys. So what I want to do now is to just briefly sketch some of the equations, because you have many of the derivations in the Jupyter notebook. But then I wanted to get as quickly as possible to the exercises. And then Karen will say something about the software. The textbook by Robert Hunt has also a GitHub address where all the programs are available from that GitHub address. So if you want to take that as a computational environment, feel free to use Hunt's GitHub address, or we will also provide you with what Karen has done so that you can look at her computational environment. And then it's up to you to decide how you want to program. We just give you some kind of frameworks which you can use or modify and use the way you want to use them. Okay? So if you now look at some further technicality, if you take a post measurement, so let me just write this down here, post measurement of a normalized pure quantum state, the post measurement normalized. Yeah. Yeah, the previous one. Oh, no. Okay. Yeah, okay. Thanks. So the post-measurement normalized pure quantum state. So this is just a definition, pure quantum state. So that means after the outcome. So this is what you're left with after the outcome. So you perform the measurement and your outcome is this lambda y. So this state is going to be given by P of I, the projection operator, and then we're going to normalize it, which means that we are going to take the square root of this quantity psi of A of P of I of psi of A. So we are collapsing the state now into a specific case. So let's look at an example here so that you get some intuition on what this actually means. So this is after the measurement has done. This is a state you have after the measurement. So it collapses to a pure state. And if we normalize it, we have to divide it by the quantity which you see here. So let's now look at an example. And again, we are going to look at this simple case which we've had, where we have just the two states in a computational basis. So we are going to make a new state, psi of A, which is given by some constant AX. So there's a vector X without specifying. So we have two states, X and Y. And then X and Y form an orthonormal basis. And then we can make a linear combination in terms of the orthonormal basis with X and Y. And that means that we have some coefficients alpha X and alpha Y. And then similarly, we could make a new one, which we just call for B. So I am getting very adventurous here. I'm just extending my knowledge of the alphabet. Like this. And then we would define one of these operators, P of X. That would now, if we now use what we have done before, this will simply be given by this outer product. And similarly, and we would have an operator P of Y, which projects out this component P of Y of Y. So we have two possibilities now. So we could get psi of A, or we could get psi of B as a result when we perform a measurement. So what we are now going to say is that the probability that we are in this psi of A is something which I just call for P. This is a lowercase letter. So I hope you can distinguish lowercase with uppercase letters here, okay? So this is a P lowercase. Hopefully the symbol is okay, lowercase letter. And since we only have two possibilities, it means that since the probabilities sum to 1, then this one should simply be 1 minus this P, right? That makes sense? If you sum them up, then you have either C of A, or if you sum them up, you get 1. So what we could say now, what is the probability of finding this lambda I given psi of A? So this should actually be given by this psi of A with P of X and psi of A. And when I do the mathematics here, this should just give us an alpha X squared. Similarly, I could ask what's the probability of lambda of I given psi of B. And if I then perform a measurement, this should now be given. If I now look at this component X, if I look at the P of X component, so that should give me psi of B of P of X of psi of B, and this should just be given by this coefficient beta of X squared. So let's look at another example and see what we will get then. So let's just run through that. I'm going to put in a new example here. So let's call this example 2 here. So we are now going to have a computational basis, 0 and 1. So we have the projection operator, which is 0, 0. And then we have the other one, which is P1, which is 1 and 1. And we know that if I now write this one, this is the same as P0 squared, which is the same as P0. And I also know that P1 of P1 is actually equal to P1. And then I make a linear combination. So I have this state psi, which is a linear combination of 0 and 1. Then I could ask, what is the probability of this psi? And now I'm going to put some kind of strange labeling of 0. So what is the probability of getting the 0th component? That means this component which you see here. So that probability should be the same. It's a kind of not optimal notation, but this is now given by P0, P0, and that is equal to psi. And if I write everything out here, so let me just do the writing out. So I would have alpha complex, so the conjugate, plus the same for beta of 1. And this is multiplied by this matrix. And finally, I have alpha of 0 plus beta multiplied with the state 1. So this is the direct write-out of that specific overlap. If I then do the calculations, you won't be surprised if we get alpha squared. So I leave that as a kind of small exercise, which means that the post-measurement state, which is normalized, so if we do that, so the post-measurement state, this state is something which I can call for psi prime of 0. So this is the one which projects out the 0th state. This is simply given by this operator P, this projection operator of psi, the original one, divided by the normalization factor. So this is now the post-measurement state, which has been normalized. So we have a normalization constant, which comes in here, P0 of psi. And when I plug things in, this is going to give us alpha divided by the absolute value of alpha multiplied with 0. And I could also, and I'm just going to give this the result for you. I could now calculate psi of 1, and that is going to be equal to beta squared, which means that the post-measurement state, which we have, with a 1 here, is equal to beta divided. So I leave that as a small exercise to you guys. So these are some specific definitions here. So what I want to do now, because I also want to speed up it, so Karen gets her share of the session. I just wanted to move back to the whiteboard, not to the Jupyter notebook, and I will give you some other expressions which are going to be very relevant and which we are going to deal with next week. And then I want to jump into the Hamiltonian type of problem which we have. So let me switch back to the whiteboard, no, to the Jupyter notebook. So what you will see is essentially the same thing which we went through on the whiteboard. You will recognize many of these expressions, and the things which we discussed about measurements, many of the same things. You will also find several of these examples. But there is an expression I want you to take a closer look at. So if you look at this probability, which I have written like this, of psi of x, you can actually rewrite this in terms of the trace of the density matrix here of the state psi, and then with these projection operators acting on it, with this one just becomes px squared. So if you look at this example here, what you will find then, if you have this one, this is your density matrix. So that will be the quantity you see here. Then we can rewrite this one in terms of that. So that means that P0 times the density matrix gives you this quantity here. If you then take the trace of this quantity, which is back here, this one, you see now that what you get is alpha squared, which is the same we got when we wrote out the equations in the other way, just now what we did on the whiteboard. So what you see here is a more compact expression for what we did on the whiteboard. And this is something which is going to be pretty handy when we are going to discuss the definition of entropies and entanglement. So entanglement plays a fundamental role, and this is a unique quantum mechanical feature that plays a fundamental role when we are going to make quantum gates and circuits and manipulate quantum mechanical states. So there are some other definitions here. And the thing, I invite you to take a look at some of these quantities because we will bring them up next week, especially the definition of the density matrix. So I leave you as a kind of mini homework to take a look at these derivations and see that you agree on this definition here of the probability, which can be rewritten in terms of the density matrix rho and these projection operators. There are some definitions of density matrices, and I just leave that to you guys. So what I wanted to do now is to bring up some quantum mechanical systems, because the first project is actually going to rotate around us writing a quantum eigensolver for these systems using quantum computing algorithms. And then we are going to look at the specific Hamiltonian, which we can rewrite in terms of Pauli matrices. And we are going to look at specific Hamiltonians, which actually are already given in terms of Pauli matrices. So that makes life a little bit easier. Now, in general, what you have when you look at a quantum mechanical system is often something defined by what we call a non-interacting part. So this could be your particles being trapped by, let's say, a harmonic oscillator potential, and they don't interact. That part of the Hamiltonian problem is something which you sometimes can find an analytical solution to. So when you do many-body physics, typically, you often look after a basis which is a solution to parts of your Hamiltonian problem. That basis, being a solution to a many-body problem, is normally an orthonormal basis. If you think of the harmonic oscillator, you have an infinity of states. Then you can use these states to build a computational basis, and then you can expand the exact solution in that basis, as we did with the 0 and 1 states. So if you go back, the whole philosophy of what we've been doing, if you now see these simple basis states, which we've been looking at. So where did I have the example here? This basis here. So 0 and 1 is what we call an orthonormal basis. And then we can expand a new state in that orthonormal basis. So when you do this kind of studies, you're often looking after parts of the Hamiltonian which you can solve in an easier way. So if a harmonic oscillator, for instance, is the dominating part of the energy, then you can think of this interaction between the particles as a small perturbation. And then hopefully the basis you have chosen is a very good basis. In principle, this basis has an infinity of states. But if it's a good basis, it would only be some few of these states which contribute to the final wave function. So searching for an optimal basis is one of the kind of what you might call a quantum practitioner's perhaps most important initial task, to find a basis which is physically meaningful and which approximates the problem to a certain extent, which means that if you calculate the energy or other expectation values, they are pretty close to what you may observe experimentally. This is normally never the case. So, but sometimes you have basis sets which are useful. And for quantum technologies, some of the systems which are very much used are so-called ion traps and quantum dots. And these are systems which ideally are confined by traps which looks like an harmonic oscillator. Actually, a Penning trap is a combination of electric quadrupole fields. And the electric quadrupole fields in two-dimensional goes like x squared plus y squared times a constant. And that is a harmonic oscillator. So these traps, which can be achieved in the lab, they look like a harmonic oscillator. And you can trap particles in them. That means that you can define a computational basis. And that computational basis is an eigenbasis of this guy. Then the whole solution is another state, but that can be expressed as a linear combination of these other states. So if we just go down a little bit, I'm going to skip this stuff, but we are going to look at a simple Hamiltonian. This is going to be a 2x2 and a 4x4 case. So in the 2x2 case, we are going to assume that there are two states. This you can think of as a one qubit state. So you have qubit 0 and qubit 1. And we are now simply assuming that qubit 0, which is the one we have defined already as an example, is an eigensolution to this guy. So we know the eigenstates. So these two states are eigensolutions to this H0. And now I'm making up a kind of Mickey Mouse example, where I simply say now that my Hamiltonian problem or my Hamiltonian matrix looks like this. So I have an interacting part, which is given by some matrix elements, and I have some diagonal parts, which is the interaction pieces. So these are the expectation values of H1 with this basis and H1 with the other state. That leads to an eigenvalue problem, which is a 2x2 matrix, which I guess you would get offended if I asked you to solve that one. So I just put up the solution. So this is just a second order polynomial. A second order equation, sorry. And here, what I've done now is actually, so one of the exercises is to take this expression here and rewrite it in terms of the Pauli matrices. So what you can do then, if you scroll down, is actually the solution to the exercise, but feel free to look at it. So if you scroll down, I take this Hamiltonian, a general 2x2 example, because we have only two basis states. And in that case, what I'm doing now, I take this H0, which is given by E1 plus E2, and I have an interacting case, which has an interaction like that. And then by simple manipulations and with the same definitions, I can actually rewrite this H0 in terms of this constant, plus another diagonal term, which is given in terms of the Pauli Z matrix. So that means that I can actually rewrite also the interaction in terms of a Pauli Z and a Pauli X matrix. So this system is ready to be simulated on a quantum computer. And this is what we will discuss in the coming lectures on how we can actually set this up in terms of quantum gates. So that would be a totally different way than us diagonalizing a 2x2 matrix. And you may obviously ask, why should we do things so complicated when we can just diagonalize? We will come back to this again and again. But you see, this is the kind of thing I want you to look at. And when you're setting this up here, it's actually pretty straightforward. And there is a simple code here. And you can see now that I'm just setting up the Hamiltonian like that. And then you can diagonalize. This is something we will come back to next week. That's an example of what we call an avoided level crossing. So I'm bringing this up because this is fundamental when you're actually going to construct quantum gates to find situations like this. I'm coming back to that. Avoided level crossing means that when the interaction is zero, then you are in the state with qubit 0. Here, you are in the state with qubit 1. This is the non-interacting energy. When you switch on the interaction, you start mixing them. So the coefficients alpha and beta, they change from 0 and 1 to something in between 0 and 1. And then you see a level of mixing. And then what happens here at this avoided level crossing is that the state here changes character. Here it was qubit 0, and here it's qubit 1. So I invite you to explore these things. And these are topics which we will come back to. So now I'm just throwing this at you and throwing you into deep waters. And hopefully I will come to your rescue a little bit later in the semester. But now you can just think of this as a computational exercise. And you can do a similar thing with two qubits. So we would then have qubit 1. And we are going to think of this as a system A and system B. So you can think of qubit 1 or one of these states, this qubit 0 here. You could think of that system A as being one of these isolated wells where you trap one particle. System B is one of the other wells. So what you would get then, if we just switch quickly back to the whiteboard. When we now look at this two-particle system, what we are going to have could be an experimental realization of a system A and a system B. And these are isolated systems where you could think of the systems as being distinguishable. They are in principle not. This is another complication when you deal with quantum mechanics. But ideally, you could think of system A having a low-lying state, which we will call qubit 0 for system A. There will be another one which is qubit 1 for system A, and similarly here. Then we can make tensor products of these two states. So we are going to define a basis now, which now contains 0A and tensor product with 0B. And if we let the 0A and B just be 1, 0, then we know that this one becomes a state 1, 0, 0, 0. This is now a 2-qubit state. So what you're going to see now is going to be a kind of idealization of actually a real system. So experimentalists are making these systems. They can trap single electrons, they can trap ions, and then they can manipulate the systems. And in particular, when it comes to this avoided level crossing, which is very interesting, this is a kind of feature you want to find in these systems in order to make quantum gates. We will come back to this, how you can actually make quantum gates from systems like that. But now, I just want you to look at this as a plain academic exercise, okay? And since we have 4 states which we can make with these ones, we will get a 4x4 matrix which we can set up. And if we go back to the notebook, what you will see then are these possible states which you see here. These are the when you do the tensor products. So this defines the computational basis. And then we make an assumption that this computational basis is an eigenbasis of the non-interacting part of the Hamiltonian. So these are eigenbases to that. And then I'm just going to make now a model. And this model has now 2 Pauli matrices, sigma x and sigma z. So the sigma z will give rise to the diagonal elements in addition to the non-interacting piece. And the sigma x will give rise to the non-diagonal elements. So this is just a very simple example, but we are going to play around with it, and it's going to be the kind of first example which we will try to implement quantum operations on. Now you can just look at this as an eigenvalue problem with a matrix, which is 4x4, and you can simply diagonalize as a function of this parameter lambda, which you see here, where we can put a lambda parameter in front of interaction. And later we are going to define, so you can run, and these are the 4 states. And when you increase the strength for the interaction, you will also get a level crossing. You can get more level crossings as well. But this example here shows you how you can actually rewrite everything in terms of Pauli matrices. And this operation here is a Pauli, the tensor product of 2 Pauli matrices, which are 2x2 matrices, gives you 4x4. Yeah. So that's this operation. And this is a tensor product of the sigma c and sigma c. And I have defined these matrices. I just defined them here. This is the Pauli X, and this is the Pauli Z matrix. So this is the way you would implement that in Python. Now, what Karen is going to do now is to show you how you can use, or how can you develop your own framework. And we are going to gradually bring in these elements. But take a look at these exercises because we will also discuss them next time. So this is just us getting started with things which we are going to reuse directly in the first project. So everything you do here enters the first project. So Karen, you want to use, we can use this laptop, is that okay? Because then I'm just going to take the, so let's just do one thing here. So we're just going to switch a little bit to Karen's software. And let me just see now, because you sent an email. Here we go, Karen. So let's just download. that. And we are going to send you this email, now this Jupyter notebook, so you can take a look at it. So let's then continue and start the Jupyter notebook. Why doesn't that function? Okay. We should have it. There it is. So I'm going to make this available to you guys online as well. So you can see the framework, and you will also get this through an email, and you will also find it at the web page. You want to take a look? You want to use this? Else they won't hear you actually.
Yeah.
So this is right.
Thank you.
This is left.
Thanks.
Put it.
Okay, so can people online hear? Oh, is noise cancellation on?
No, so there's no close cancellation.
Okay, sorry. Can people online hear me?
Yes.
Yeah, I just great.
Yeah, we can.
Great. At this point, it's not much of a framework. I just put in sort of the minimal requirement for building, say, a quantum computer simulator. But first we have to think of the structure. Then I just wanted to ask if anyone could tell me where the information of a quantum system is stored in. So, yes, yeah, and or as we would say, a state vector, right? And through what do we interact with the quantum computer? Like, how do we manipulate these qubits? Mm-hmm. Yes, that's very technical, but I was thinking more like gates. Right. Yeah, because we're writing a simulator, which means we completely ignore the physical world, essentially. So basically, we have to have the state and the gates. And for a 1 qubit state, we have just 1, 0. And the reason that, yeah, they have to be complex. And then we have the gates, the identity, Hadamard gate, and the poly gates, and then the phase gate. Now, one thing that's important for quantum gates to have is that they have to be unitary. So there's just these functions to test them. And now if we are running, and then we'll see that the S gate is actually not Hermitian. So if anyone could tell me why the phase gate is not Hermitian. Yeah, here. Like physical reasons why the phase gate is not Hermitian, if anyone remembers from quantum mechanics. Right, because a Hermitian gate means it's an observable, and phase is not an observable. You cannot, because it's e to the I phi, and it will always, when you measure it, it will always go to 1. But that's okay on a quantum computer because we only want them to be unitary, and they don't have to be Hermitian. Right, and then I think the next exercise is to apply the Hermitian, the Hadamard gate on a qubit. So we can just do that. And here I just wrote a function to sort of visualize it. So it looks like how you write in bracket notation. And then the measurement in principle would destroy a state, and then you sort of have to prepare the state every single time you do the measurement. But because we're writing a simulator, we don't care. So we can just define sort of the number of shots. So if I now have one shot, then you can see, oops, did I write this? Right. Yeah. Yes. If they have one shot, then you don't really get anything, right? You just get, okay, you get 0. And you can't really see the difference between the 0 state and the Hadamard state. Yeah, right. Okay, so here we have basically, okay, if you read here, that's what it returns. So if it's a string, then it tells you which qubit it's, so it's like 0 that you measured 0, and then there's one measurement of 0, and then here it's that you measure 1, and that's 0 of it. It will make sense if we increase it to say 100 for now. Then if we're in the 0, in the 0 state, then we always measure 0. But it's different if we apply the Hadamard gate on it, then we have sort of 50-50. But right now we're sort of like from you can see the state vector, but if you're running it on an actual quantum computer, then that's all you have, the measurement results. So you have to use these results to sort of reconstruct the state because you can't see the coefficients. So in principle, if you have more shots, then it would get closer to the actual coefficients.
Which you should have done. And that's one of the problems for the computers actually. You get the values of the computer, and this is something to demonstrate. You will see then that you will get, because this is getting closer to 50-50, but if many people are running real quantum computer, there may be terminal expectations, because the system gets it. Then you're going to computational basis. And then you can risk after you're getting results which are far away.
Right. And then now, yes, go back to the to 2x2 Hamiltonian. Oh, right. Sorry, I forgot about this. So yes, you have hopefully more than one qubit eventually. So like what happens when the system grows? If you have 2 qubits, what does the state vector look like? Or like what's the size of the state vector? Yes. And if you were to apply a say a poly-Z gate on a 2 qubit system, what would you have to do? So you want to apply the Z gate on the first qubit. Yes, exactly. Great. So these are things to keep in mind when you write your 2 or more qubit systems. And then lastly, I've just written down that any 2x2 matrices can be decomposed into polymatrices because they form a complete basis together with identity. Yep. So good luck with the exercises.
The last part is your solution.
Yeah.
We just want to start with and start thinking of how you want set up these systems. And in the beginning, you could just diagonalize to standardize solvers. And then we would gradually move into how we can represent these qubits and how we can represent them. So these are the kind of steps we want to give you before we present the full project. Everything we do here will be an element of the project. So everything can be used. So the exercises which we give, they are meant to also give a good start for the project. And the idea there, as far as I saw from many of you, is more to try to simulate and implement an algorithm which is called the relational quantum algorithm, which is one of the more used ones. So the quantum problems with quantum computers nowadays. Cool. Thanks, Gary.
We're going to stop here now, and you will get the kind of update with videos and everything and plans for next week. Hopefully I will have the slides ready by the end of the week so you can look at them over the weekend. I guess you don't have any spare time problems. Okay, guys, thanks for coming. It's a great pleasure to meet you all here. For those of you online, I'm going to stop the recording.